In this unit, we're talking about acids and bases, and we need to come up with some definitions. Now, the simplest one is this definition by this guy named Arrhenius. And Arrhenius basically said that an acid looks like this, that it basically is, and I feel like this should write, but it's not. There it goes. Now it's writing. So an acid looks like this, HA, right? Now, A is a fictional ion, right? But it means that it has H plus, right? If you remember from when we were naming things, if I put H at the beginning of a compound, that means it's H cation, hydrogen cation, and so has H plus ion is what is a good definition for an acid. Another way of looking at it is that it creates H plus ion in water, but we're going to focus mostly on just the idea that if we look at the formula, we can tell if it's an acid because it has H plus. So when you see an acid, you think of things like HCl, right, which is H plus and Cl minus, right? If you think of H2CO3, right, you have H plus and bicarbonate ion, HCO3 minus. So you have these things that have H plus ion in them. Now you might have something like CH4. CH4 doesn't have H plus. There's no H plus, right? Because the H is written afterwards, and so this is not an acid. Okay? And so that's our way of signaling that we have an acid that has H in front. Now a base is the same basic concept, except it has OH minus. So when we see a base, we should see something like NaOH, right? Because it has Na plus, which is just a spectator ion balancing out the charge, and OH minus, right? So it creates a hydroxide ion. So bases create hydroxide ion, acids can create H plus ion. So if we were looking through, say, a practice problem such as this one, and we were looking for Arrhenius acids, what we're basically doing is we're looking for H plus. Right? And if we're looking for Arrhenius bases, we're looking for OH minus. Right? And we can see it right here. We can see here's an acid and here's a base. Right? Now there are other ones also, right? But right? But we can see something like this, where this is written second, and this is neither an acid nor a base. Okay, so this is not H plus. Surprisingly, when we look at this one, this is not OH minus, right? Because what it's bonded to is CH3. This thing is molecular, not ionic. And so bases have to be ionic compounds because they have to create OH minus, which is an ion. Okay, so you need to be careful about that. Now, there is a second definition for acids and bases created by these two people named Bronsted and Lowry. This is a definition that's based on action, not on identity. It's a much more powerful definition because it implies that an acid is something that donates H plus. And so if I look at a chemical reaction, I look at what's happening, then I can see whether something is acting like an acid or acting like a base. And so we're going to say that an acid is an H plus donor, right? So acids donate H plus, right? Notice that it says donates a proton. A proton, we're going to use this idea of a proton, right, which just means a positive ion from the nucleus. Now, if you recall, hydrogen, right, if we have H, all it has is one proton in the nucleus, and it has one electron, right, one negative ion orbiting the nucleus, right? So hydrogen just looks like this. Well, H plus is that same picture, but it's without the electron, so it's just my H plus, just my proton. So H plus and a proton mean the same thing. We're also going to see that we use an aqueous proton. When I say H plus AQ, I also call it H3O plus. And that's because in water, H plus doesn't exist by itself. It tacks onto the side of a water molecule. And this H3O plus is called hydronium. And so since almost all of our reactions will take place in water, you're going to see that we use proton and H plus and hydronium to some degree interchangeably, because that's what acids create in the presence of water, hydronium ion. So an acid has a proton or an H plus, and it creates hydronium in water. But anyway, I'm just warning you that we're going to say proton a lot, we're going to say hydronium a lot, and you need to know what we're talking about. So an acid creates this, a base, right? A base accepts a proton. Notice that there's no mention of OH minus because other things can accept protons besides OH minus. In the example, we have NH3. NH3, you can see, goes to NH4 plus. And so this is accepting an H plus. And since it's accepting H plus, NH3 is a base, right? Now, the source of the H plus was HCl. And since HCl, right, the H started here, right, and then the H popped off and went to NH3, this is our source of H plus, and so this must be our H plus donor. And so when we look at the process of a chemical reaction, we can see the Bronsted-Lowry acid and the Bronsted-Lowry base. Okay, but you need to have a reaction to really identify Bronsted-Lowry acids and bases. Now, one way of identifying a Bronsted-Lowry acid and base is to put it in water to do what's called hydrolysis. And hydrolysis means reaction with water. Hydrolysis. And hydrolysis. I think that's right. It seems wrong somehow, but let's just call it right for a moment until I scroll down and actually look at the practice problems where I've written it properly and where I'm not. Hydrolysis. Ah, got the Y and the I backwards. Sneaky. Better. So when we have hydrolysis, we can take a weak acid. So if I take something like HC2H3O2, and I can put it in water. I don't want to copy an image. Really? And I can, oops, right? I can put it in water. If this is an H plus donor, what it creates is H3O plus. In other words, the water accepts that proton, right? Remember I said in water, H plus is H3O plus. And then what's left behind is everything else, C2H3O2, with a negative charge because it lost that positive charge. And so this shows, hydrolysis shows a weak acid acting like an acid, and we can do the same thing with a weak base. If we have a weak base present, let's see if I have space for it down here, right? Again, I can do hydrolysis for a weak base, and this time I can learn how to spell it properly. And so I can take a weak base like, say, Cn minus, and I can put it in water. And if I do that, it accepts a proton from the water, right? And so it creates HCN. See, it accepted that proton. Well, whatever's left behind is water without its extra H plus. So it makes OH minus in water. And remember that bases create OH minus in water, and acids create hydronium in water. So hydrolysis reactions are a way of showing that. Now, there's a third definition based on the work of this guy, Lewis, the guy who did Lewis dots. And he said that acids are electron acceptors and bases are electron donors. And you'll find, if you actually look carefully at any reaction that we draw, that the acid in this reaction is in fact accepting a pair of electrons. For example, this H plus from water is accepting the extra pair of electrons from Cn minus, so it's acting like an acid. Cn minus is donating that extra pair of electrons that it had to the H plus, and so it's acting like a base. So Lewis's definition is the most general. Bronsted and Lowry is smaller. It's limited to things that accept and release H+. And then Arrhenius is the most limited because it's based on the identity of the compound itself. All right, but we're going to stick to mostly Arrhenius's definition and Bronsted and Lowry definition, Bronsted's and Lowry's definition. All right, let's practice a little bit and see what we can do. So if we look at this reaction here, it says, is this an acid-base reaction? Well, if it's an acid-base reaction, I'm looking for an H+ to move from one compound to another. And if you look, here's an H+, and it's going to a new compound. It's starting with C2H3O2, and it's ending up with Cn. So this is definitely an acid-base reaction, right? If I'm looking for something that's not an acid-base reaction, if I look at this one, right, look at this. There's no H+ being transferred at all. So this is an ionic reaction, but it is not an acid-base reaction at all. There's no H+ moving. So as far as Bronsted and Lowry are concerned, this is not an acid-base reaction. Which compound is acting like an acid up here? Well, you can see the H is starting out with C2H3O2, and then it's leaving it. So HC2H3O2 is our source of acid. Which ion is acting like a base? Well, Cn- is accepting the H+. Notice I don't worry about the K. The K is what I call a spectator ion. Okay, it is just there to balance the charge. So when I ask what ion is acting like the base, I actually have to know what ions I'm talking about, and I might need my ion sheet. And I would find that cyanide ion is one of the ions on that ion sheet. It has a negative charge, and it can accept the H+. And that's why I have HCN at the end. Okay. So let's go on and do a few more problems. A few things that we need to know. There are acid properties and base properties. You probably talked about them in middle school. Right? We've already talked about a few of them. Acids typically contain H+, create hydronium in water. A few other things, they taste sour. You find them in things like sour apples, like green apples. And the sour acid in green apples is called malonic acid, which comes from the Latin for apple. Citric acid, right, which is the acid in oranges, grapefruit, and lemons. Acids have a pH less than 7, and you're probably aware of that they have low pHs, and we can test them with a pH meter and things. There are acid-base indicators that we use. We've already used bromocresol green in the lab, and we know that in the presence of acid, it turns yellow. Phenolphthalein is another acid-base indicator. It is actually colorless in the presence of acid, right, and pink in the presence of base. Litmus is red in the presence of acid and blue in the presence of base. And you may have heard of things like a litmus test. And a litmus test means something that's either this or that because it comes from acid-base testing where it's either red or blue. Acids also react with active metals. So we think of acids as being corrosive because they can react with active metals to release hydrogen. Okay, so we've got these properties for acids and bases. One that's kind of funny is that bases taste bitter, like acids taste sour. And if you don't believe that, you can always lick a bar of soap, or you can just go into your kitchen, wet your finger, dip it in some baking soda, and then simply lick it. It's not going to harm you, but it will taste quite bitter. And that'll remind you that bases tend to taste bitter. Okay. Now, there's this definition that we're going to use, strong and weak. And this is a weird idea, strong and weak, because we usually sort of confuse it with people strength, right? You know, we say, strong, it's very, I don't know, brutal or something. But strong simply means it breaks apart 100%. So when I see a strong acid, I tend to draw this arrow because it goes to products 100%. In other words, when I dump HNO3 in water, I actually have none of this left, right? I have 100% of the products. In other words, it's all H+ and NO3-. So if I have a bottle that's marked 1 molar HNO3, it's kind of a funny label because it's actually no molar HNO3. It really should be labeled 1 molar H+ ion, right, and 1 molar NO3 minus ion, because it's completely broken apart into those two ions. Okay, that's a lot of H plus, by the way, 1 mole per liter. That's a fairly concentrated acid. However, if I have a weak acid, then I draw these equilibrium arrows, and that's because weak acids have K values, right, that are much smaller, right? And so the K value for carbonic acid is something on the order of 10 to the negative 8th or something like this. I can't remember what it is, but it is actually I could look it up pretty quickly. Let's actually do that. We'll just type Ka carbonic acid, because I would like to actually know the number. And the first Ka value is 4.5 times 10 to the negative 7th. Okay, so let's go back to that. So K is 4.5 times 10 to the negative 7th for the first H that comes off of carbonic acid. That's a really small number. That means that essentially it's almost 100% this. It's mostly still carbonic acid. And there's very little H plus, right? And so if I had 1 molar, if I could create 1 molar H2CO3, right, then it's basically 1 molar H2CO3 and just a little, right? It's basically, it stays this with just a little H plus ion and just a little bit of HCO3 minus ion. Okay, so it breaks apart just a little bit. Now, it can actually react just as much as 1 molar HNO3. It just takes longer because when I take away some of this H3O plus, right, in the reaction will continue to shift right to replace it, right? So it can still react just as much, but it reacts much slower. And so because it has less H plus, the reactions will be slow. Right, the reactions will be slower and the pH will be higher. Whereas here, the reactions will be quicker. Because all of the H plus is available right away, and the pH will be lower. So that's what we mean by strength. Now, how do you know what things are strong and what things are weak? Well, there are lists, and here are lists. A list of strong acids and a list of strong bases. And if you were to look at this, you can see some patterns in this. You'll notice that these are all halogens, right? And so halogens are so electronegative that they pull electrons off of H+. The exception is F. F is electronegative, but it actually bonds covalently with H. The exception is F minus, right? So HF is a weak acid. Then we have the elements that are kind of electronegative, and if we tack on enough oxygens, they can be electronegative. And so we get the elements that are around F, right, H, S, and Cl, with as many oxygens tacked on as possible. And so you'll see that we have the halogens all the way at the right of the periodic table, and then nitrogen, sulfur, and chlorine with the maximum number of oxygens. For bases, we need things that will give up electrons because we need to create OH minus. And so these are all group 1. Right? If they're all the way at the left, they have very few protons holding their outer electrons on, and they give up electrons to hydroxide quite easily. We also have the bottom of group 2. And again, when you're at the bottom of the periodic table, you give up electrons very easily, and so these guys also create strong bases. You would assume that of all of these bases, the one that gives up electrons the most easily would be cesium hydroxide. And in fact, cesium hydroxide does give up electrons really easily, and cesium hydroxide, if you could differentiate these bases, cesium hydroxide would be the strongest. All right, we can look at some practice problems. Again, if we're looking for areneous acids, we're looking for H+. If we're looking for areneous bases, we're looking for OH-. So H+, well, here's an H+, and here's an OH-. So we know that there's an areneous acid and there's an areneous base. And we can find other ones like it. Over here, we're looking for Bronsted-Lowry acids, and Bronsted-Lowry acids are H+ donors, right? And Bronsted-Lowry bases are H+ receivers, or acceptors, right? So if we look over here, HCN is the beginning of the H. The H starts with HCN, and so here it is, HCN. Our base, the thing that accepts it, is the OH part of calcium hydroxide, right? It starts out as OH and ends up as H2O. So our base is OH-. Now, is it always going to be hydroxide ion? No. If you look in the second one, NH3 is taking the H+, right? It starts as NH3 and ends as NH4. So our base is NH3. Over here, H2SO4 is where the H's are coming from, right? You can see SO4 is without an H over here. So H2SO4 is our acid. Okay. If we continue with this, if we're looking for strong and weak acids and bases, well, over here, this is one of our strong acids, right? Well, this looks like an acid, but it's not on our list of strong acids, so it must be a weak acid. Right? Over here, we have one of our strong bases, right? Over here, we have something that contains hydroxide, but it's not a strong base, so it must be a weak base. Okay? And so we can do it that way. In other words, you have one way of figuring out how do we know which ones are weak? Well, they're the bases that aren't strong, or the acids that aren't strong. Turn phenolphthalein indicator pink. Hey, that would be a base, right? Taste sour. That sounds like an acid. And so all what this is another way of asking the same question over again, right? But it's taking you back to that chart and trying to get you to remember some of those properties. Now, let's write a hydrolysis reaction. And a hydrolysis reaction means that we're adding water. So in both cases here, I'm going to add water. The difference is, in one case, I'm looking to show that something is a base. So this is an H+ acceptor. Well, if NH3 is accepting an H, that means H2O is losing an H. So H2O, when it loses an H, becomes OH-. Well, NH3, when it accepts an H, becomes NH4+, because it's NH3 plus H+, right? Don't forget the charge. So NH4+, because it starts at 0 and adds an H+ ion. So that would be the hydrolysis of ammonia, right? If I want to do the hydrolysis of sulfurous acid here, this time the weak acid is an H+ donor. Well, if H2SO3 is donating an H, something has to take the H. So water in this case has to take the H. And when it does, it becomes H3O+, which you might recall is called hydronium ion. A OH- is called hydroxide, and these are names that are going to come up a lot, so I keep on repeating them. Okay. What's left behind? Well, we took an H away from H2SO3, so now we have only HSO3. We took one of its H's away. Because we took a positive away, and it used to be 0, it is HSO3-. So you always have to be careful of the charges. Okay? And if you're really confused, draw yourself a number line. That's a really good way of remembering what's happening when you're subtracting and adding numbers. All right, well, that's the end of this worksheet, and hopefully this has been helpful.